Okay, well, you had some great questions after the first the morning's talk and after the break. So during the break, so let's talk a bit about how this fits in, or how cloud computing fits into this story. So we're basically approaching this question from the perspective of the enterprise, right? So you're a large organization. Here's your application, right? Anybody been there? Spaghetti. Does this look like anybody's application? Okay, so we're going to move this to the cloud. Okay, now watch closely. This is very important. You pay your consultants millions of dollars to do this for you, right? We're going to move our spaghetti code into the cloud. There we are. We just put our spaghetti code in the cloud. Well, there might be more to it than that, right? The cloud isn't just some sort of big server in the sky. We can just stick spaghetti code in and expect to get all these wonderful benefits of the cloud. Let's say, though, that it's not quite spaghetti code. It's not quite that bad. Here's our app, right? We wrote it in Java or C#, following all sorts of OO best practices, right? Completely modern application, right? But now we want to move it to the cloud. Okay, so let's see how that works. Well, there we are. Java in the cloud. Right? Works fine, right? Well, the problem is that you can't think of the cloud as just some big server in the sky, and all you have to do to move some existing capabilities to the cloud is just stick it in the cloud. There's more to it than that, and that's sort of the focus of this talk. So the point here is that you need to architect or re-architect your existing application if you want to take advantage of the benefits of the cloud environment. So the key advantages of the cloud that differentiate cloud computing from, say, traditional managed hosting is elasticity as well as fault tolerance. So elasticity is the most important, right? The idea of elasticity is if you need more capacity or capabilities from the cloud, you get more in an automated way. So you automatically provision more capacity, and then when you don't need it anymore, it's deprovisioned, again, automatically. So it expands and contracts as needed. And then fault tolerance as well, right? If part of the cloud goes down, and you expect that to happen, you expect failure in the cloud, but what happens is that it should be able to come back up in an automated fashion. So if you have a cloud instance and it goes down, the cloud should be able to reprovision a replacement instance, again, in an automated fashion. But if your application isn't architected to support these capabilities, it's not going to be able to take advantage of them. If anything, the cloud is going to make your application worse, not better. So this is a key part of the cloud computing story. So essentially, elasticity is what makes clouds cloudy. That is what differentiates cloud environment from a traditional environment. So this diagram basically shows the key elements of cloud computing. We have the deployment models at the top, private, public, community, and hybrid clouds. We have the key core service models, software as a service, platform as a service, infrastructure as a service. Then we have essential characteristics. There's 5 of them here, and I'm highlighting rapid elasticity, but there's a lot more to cloud computing than just elasticity, and then quite a number of others as well, right? And service orientation is one of many. So cloud computing has a lot of different characteristics, but elasticity is one of the essential ones, and that's the one I'm going to be focusing on. So the challenge with elasticity is that we want to be able to provision more capacity, whether it's storage, virtual machines, or if we're running a platform as a service, we want platform capabilities, or software as a service, we want more software capabilities in a rapid and automated way, right? So cloud computing is not, we need another server. Make a phone call to your provider and maybe you get it in 30 days. Because somebody has to go and do something by hand. That's not what we mean, right? What we mean is that it's automatic. The cloud provider has already set that up to provision that for you. It's measured, right? You pay as you go if you're using a third party, a public cloud. So they measure how much your utilization is, so you only pay for what you use. Even if you have your own private cloud, you still have measured usage, because that's how large organizations essentially handle the financing for their private clouds, because they measure which departments use which capacity. And then scaling down is every bit as important as scaling up. Right? If you misuse the cloud, what often happens is that it's great, you can provision new virtual machines whenever you need them, but then you have no way of knowing whether you're done with them, so they stick around forever, and you have these ghosts, these zombie machines out there, and you have more and more and more of them because you have no way of knowing when to turn them off. Well, you're not going to get the cost savings benefits of the cloud unless you are able to scale down as well. So keep in mind, you don't necessarily know ahead of time how many of these instances you're going to need. Because the whole idea is that the cloud supports a level of unpredictability. Right? You don't know what sort of spikes and demands you'll have, and that's why you're moving to the cloud. Right? If you could predict the demand for capacity efficiently ahead of time, then maybe you should just buy servers, because then you'd only buy exactly what you needed. But the reality is you don't have that information, and that's why the cloud is so valuable, is because it deals well with this unpredictability. Okay, so one of the challenges with cloud computing, when we talk about architecting for the cloud, one of the key differences between the cloud environment and the traditional on-premise environment is the fact that the cloud environment is what we call partition tolerant. That is, we have multiple instances, and any of those could be running or not running at any particular point in time. So if we have a partition tolerant environment that is highly available, we cannot achieve immediate data consistency. And this is a proven theorem called the CAP theorem, that immediate consistency and partition tolerance and availability, you can only get two of. You can't get all three. So in a cloud environment that is inherently partition tolerant and available, we need to give up immediate consistency. All we can expect is eventual consistency. That is, our data may be inconsistent for a short period of time until we synchronize our data, and then it's consistent. So we actually had a question about rollbacks a moment before the break, and this ties into that, right? Because traditional databases are ACID compliant, right? Atomic, consistent, isolated, and durable. Those, to be ACID compliant, you have to be partition intolerant, because in a partition tolerant environment like the cloud, you can only achieve eventual consistency. Okay, so partition tolerance, here's the definition, the formal definition, right? A distributed system is partition tolerant if it will continue working even in the case of a partial network failure. Right? Bits or pieces of your deployment might fail or stop communicating with each other. It may simply be a network issue where they stop communicating, or it could be an actual failure, but the overall system will continue to work. Well, this is critically important with the cloud because you expect this to happen. Right? You expect individual instances to fail or stop communicating now and then, and the last thing you want is for your whole application to crash and burn every time a single virtual machine has an issue. Right? So that's why partition tolerance is so important, and architecting for a partition tolerant environment is so important. So even though you could theoretically have a cloud environment that's all in a single partition, cloud environments are inherently partition tolerant because that's how you get the elasticity benefits of the cloud. So I don't know if anybody recognizes this movie still, a little movie trivia for you. Pretty obscure. This is the movie Brazil, remember that? So he's pulling the table through this partition because there's somebody on the other side pulling it the other way. So he's not very partition tolerant. Anyway, okay, so to run ACID transactions, we need a partition intolerant environment, right? It all has to run in a single partition. And if you have an enterprise database, say an enterprise installation of Oracle or something like that, it'll run in a single partition. And so it's all about vertical scalability, right? You can throw more hardware on it, and you essentially have, if you have multiple Oracle instances, they have to synchronize in a sophisticated way in the context of a single partition. Well, in a cloud environment, since we don't have a single partition, we can't do ACID transactionality. So what's the alternative to ACID? It's called BASE. I didn't make this stuff up. ACID, BASE, get it? Anyway. So what does BASE stand for? Basic availability, soft state, and eventual consistency. So basic availability, right, is the ability to support partial failures that don't lead to a total system failure. That happens in the cloud all the time. Soft state means that state information has to be allowed to expire, so we have to continually refresh it. And then eventual consistency, right? Data may be stale some of the time, and it's okay to use stale data because we'll be able to synchronize our data and update it after a certain amount of time. So BASE actually predates cloud computing. It's been around for a number of years. And if you think about it, BASE behavior is familiar in many web-based applications. So for example, have you ever wondered why when you do a Google search, comes back and it says approximately 100,000 results or something like that? Right, well, why is it approximate? I mean, hasn't Google indexed the whole internet? Why can't they give you an exact number of hits? Don't they know the exact number of hits? The answer is they don't. Why? Because they only have eventual consistency. Right? If you run the same search at precisely the same time on different parts of their network, you'll get different answers. And that's why they can only give you an approximate number, because their data are never consistent. They never have an exact count of hits for anything, because they have a partition-tolerant environment. So soft state is familiar from instant messaging buddy lists. Right, so if you're using your instant messaging buddy list, so you have your phone and you see the little smiley face, it means your buddy is available, right? But let's say then the buddy's phone drops off the network, or their computer crashes, or they just quit their application. That little smiley face will stay a smiley face for a little while, right? Because it didn't get a message from your buddy saying that I'm leaving. Their phone just went off the network. So that little smiley face will stick around for a minute, 2 minutes, 5 minutes, and then it eventually says, oh, wait a minute, I haven't heard from your buddy in a while, they must not be available, right? So that's what we mean by soft state, right? We don't necessarily know at every point in time that your buddy is there, so we expect state information to be refreshed periodically, or it expires. So those are some of the behaviors that we're familiar with. Essentially what we're saying is in a cloud environment, base is the most we can expect from our transactions. If you've architected your application with ACID transactionality in mind, it's not going to be able to take advantage of the benefits of the cloud. So you have to think about, well, which do you want? Do you want that high level of transactionality, or is base level of transactionality sufficient to meet your business needs? So, inconsistent data, right? Here's a little example, right? If we have an inventory management application, well, the whole point to an inventory management application is keep track of the number of items in inventory, right? That's what that thing is for. So we move that thing into the cloud, you may have inconsistent data, right? So two people can query the same number of widgets and get different answers at the same point in time. Well, that could be a problem if somebody is trying to order that last widget, but actually somebody else got it, and your data are inconsistent. So what would we do? Well, does that mean we can't run our inventory management system in the cloud? Well, no, not necessarily. What it means is we have to plan ahead for this, right? We have to say, well, there's some sort of threshold, right? Maybe if we get below 50 widgets in inventory, we don't necessarily know if any are available or not. So if somebody tries to place an order, we have to change the behavior of application to say, we think we can give you an order, but we'll let you know in the next half hour if we can actually fulfill your order, or if you have to back order this item. And then eventually you synchronize your data and let the customer know whether or not they actually got their item. So you have to change the behavior of your application to support eventual consistency. But eventual doesn't mean never consistent, it just means you have to wait a certain amount of time until you can synchronize your instances. And it's up to you how you handle that synchronization and how often you do it. And that becomes a performance issue, right? So it's just like expiring cache data, right? If you expire your cache data every millisecond, your cache isn't going to give you any benefits. It's going to slow you down. The whole point to a cache is to resolve some performance issues. Same thing with synchronization, right? If you do it too often, it'll slow everything down. If you don't do it often enough, your data will be inconsistent for too long. And now it's up to you as an architect to decide, what's the right balance. Okay, so state information. This has been a key issue from this morning, right? A key part of the REST story is moving application state information to the client, right? This is a key part of the cloud story as well, because if we have this cloud-based application, right, we might have the persistence tier, which may or may not be in the cloud, so that's where we store our data. So we have to ask ourselves, what happens if that's partition tolerant. And we have the application tier. Those are the virtual machine instances running our application. And we want to be careful about putting state there because it won't scale if we put state there. And then we have to think about putting application state on the client, which is HDOS, right? Moving state information to the client. But it requires this architectural approach where we have hypermedia as the engine of application state. But the key question here is, what is the problem with using that middle tier, the application tier, to maintain state? Because that's how applications often do it, right? They store application state on the database, but while you're running the application, they put it in the application tier, because as somebody mentioned, you don't want to rely upon the client for too much, because the hackers will get in and screw things up. So does that make sense in a cloud environment? Well, keep in mind that REST provides explicit state transitions. Right? Click a link, changes the state. Hypermedia is the state engine, right? Because REST is conceived of in an HTTP context, and HTTP is essentially a stateless protocol. Well, we do have cookies, but we don't rely on cookies because your clients can always turn off support for cookies, right? So we essentially assume that from one request to the next, the server's forgotten all about us. Right? So we're trying to deal with state in this environment of statelessness. So essentially what we do is we rely upon the server to maintain resource state for any state information that applies to all clients, and we rely upon the client to maintain application state because that is fully scalable. So and then we manage state through the hyperlinks. So let's see how this works in the context of the cloud environment. So here's your application before the cloud, a traditional distributed application, right? We have 3 tiers represented here, right? A persistence tier on the bottom, our application tier, our client tier. Okay, so how do we deal with issues like scalability and state? So in a traditional world, we have a number of scalability approaches, right? In the persistence tier, we can do database sharding, database virtualization, a number of approaches of scaling our databases. On the application tier, we can do clustering, we can do load balancing, so there's a variety of ways of scaling that as well. So we have a number of traditional approaches, and of course N-tier architectures can be very scalable, and we pretty much figured out how to do that. So how do we maintain state in a traditional distributed environment? Well, we can persist state in the database. So as Atul was talking about, we could write our state to the database, but if we do that every single time, it limits our performance. So we only want to do it now and then because it's such a, it doesn't scale very well, especially if you have lots of users. We can maintain state on the middle tier with session beans or threads or session cookies, right? But the whole idea of using a thread on an application server or on an ESB to maintain state is that, what if the thing crashes? Just as Atul was talking about. Well, you have to write the thread state to the database periodically, and then you have all those issues with either performance or with fault tolerance, right? If something goes down, you've lost your state information. Or we could use cookies, say, on the client tier, but there's problems there because you could turn off cookies and you don't necessarily have universal support for them. Okay, so here's your application in the cloud. So notice what I've done here. Instead of having a certain number of databases, well, we have a flexible number of databases, right? Because we could potentially be putting that tier in the cloud. So we have more or fewer server instances storing data as needed, right? So whether we're using Amazon S3 for dynamic storage, or using Hadoop in a big data environment where we're distributing data over multiple instances, where we have more or fewer depending upon what we need. The application tier, same thing. We have more or fewer virtual machine instances running our code, and we have as many as we need. We don't want to put state there because we would have issues with fault tolerance and scalability. And then we want to push application state to the client because we can use the HADOS constraint of REST. So the key challenge here is avoiding state on the middle tier and only using a persistence tier for resource state and not putting application state there by mistake. And that's going to be the key parts of the story. So here's how it works. This is the best slide. This is the climax of this morning's presentation. So here's how it works. Let's say we're on the Amazon shopping cart. We're on the Amazon website and we want to use the shopping cart. So here's the client. They need the shopping cart, right? Because they want to buy a book or whatever it is. So make a request of the Amazon server. And what does the Amazon site do? Well, it spawns a cloud instance to handle this particular customer and their shopping cart today. Populates that instance with any information it has about that customer. That's part of the resource state. So Amazon maintains resource state indefinitely, right? You put something in your shopping cart, come back 10 years later, it's still in your shopping cart, right? The price has gone up, but it's still there, right? Well, of course, that is obviously written to a database somewhere, right? It's pretty clear. So that's stored there. What is also stored there is the logic for the shopping cart. So the whole shopping cart application, all of the logic, is essentially part of that resource. So when the customer comes to this website, it spawns a cloud instance and bootstraps it with the shopping cart application itself. But that shopping cart application, I'll draw a little, flowchart diagram there. Essentially, that is stateless, right? Because it's the same application for everybody, and it's populated with whatever that initial state information is for this customer, whatever the shopping cart has in it when they begin. Okay. So now that virtual machine instance, that shopping cart instance is now acts as the server. So it acts as the client with respect to that persistence tier in order to get the initial application. Now it acts as the server, and the customer now interacts with that instance. And they conduct the shopping cart interaction solely with that shopping cart instance. Now, if the Amazon needs to scale, right, because they have millions and millions of customers, right? Well, all the customer is doing is clicking links and completing forms, right? Basically, working through the application where hypermedia, that is the website, all its links and all its forms, is the engine of application state over here, right? So if the Amazon needs to scale, it can spawn a new instance of that middle tier. Now, it doesn't matter to the client which virtual machine is serving its requests, because the client, the web pages, the representations, have all the state information. Those are contained in the messages that are being exchanged between the client and this middle tier, which is acting as the server. So just like Atul was talking about, the state information is maintained in the messages. So if you view source, you'll see it right there in the hidden fields in the forms that are being submitted every time you click a link, right? So that's where it's being kept. And it's not being maintained, the state information is not being maintained in the middle tier. So that if the client is directed to a new instance, it doesn't matter, right? Because one instance is just the same as another, right? They have no idea which customer they're serving or where they are in their particular shopping cart process, because that information is being maintained on the client. Okay, so let's say that nothing goes wrong, they complete their transaction, and at the end, they submit their credit card, and that obviously executes the transaction on the persistence tier. That's part of the resource state. That their credit card has been approved, and that the product is on its way, and Amazon's inventory is adjusted to account for the purchase. That happens on the back end. That has to happen there. But the shopping cart application is running on the middle tier as much as it can. Okay, so that's the happy path, right? Nothing went wrong. Let's say something does go wrong. Let's say that box that the customer is interacting with crashes in the middle of the shopping cart. Right, as Atul was talking about, that's the nightmare scenario you want to avoid, because you're in the middle of something, and if it crashes, the last thing you want is for your customer to not know what state they're in, or to have spent 20 minutes populating this cart, and then they have to start over, right? Okay, so it crashes, bam, okay. So the cloud instant crashes. Now what happens? Well, the backend says, oh, wait a minute, this instant crashed. So it spawns a new instance with the same representation. So that little application representation, all the web pages and all the hyperlinks, is put onto the new instance, and the client, customer, continues, because all of the state information is maintained in the messages, which are essentially the representations being sent to the client, where the document is the message. So it's a message. When it's on the way to the client, it becomes the representation, the web page that the client is interacting with. So as a result, this is really the only way to take advantage of the elasticity benefit of the cloud when you have this kind of application. So it doesn't apply to every kind of application. It only applies to hypermedia applications, like Shopping carts, obvious case, right? Where we essentially have a customer, have a user interacting with a set of web pages that are connected via hyperlinks. That's a hypermedia application. If your application isn't like that, this doesn't apply. So it doesn't apply in every situation, but it applies in a lot of situations. So one of the challenges with state on the middle tier is the problem of the matrix. I like this. Remember the movie The Matrix? So the story of the Matrix, right? The Matrix is this illusion world, and what are they trying to do? Well, they're trying to find Neo, right? The main character, because Neo is the one, right? He's the only person in the Matrix who is real. Everybody else is imaginary. Remember that? Well, if you maintain state on that middle tier, then only one of those instances is your instance. Right? Each customer now has one instance that is their instance because you've instantiated some object and put it on that machine, and now that object instance is now what the customer is interacting with. So if something goes wrong, you have to not only recreate it, you have to find it. Right? This customer, if their state's on the middle tier, the customer has to find their instance. Right? Because their instance is different from everybody else's, right? And it's just like finding Neo in the Matrix, right? You have all these aliens trying to, get you. It's difficult, right? So if you don't maintain state in the middle tier, then any instance will do, because all the instances are the same, because the application state is maintained here, and the middle tier knows how to update resource state as needed, but only do so as needed. It will not update application state on the back end until it's time to do so. So that's the power of taking a REST-based approach in the cloud, is it gives you the ability to move state to the client as needed. And that's what REST is all about. When we say representational state transfer, we mean we're moving state in representations to the client. And that's why it's called that. All these developers saying, what the hell's up with the name, REST, representational state transfer? What the hell is that? That's what the whole point is. And it's interesting that you need to do that in order to take advantage of cloud environment when you're trying to support a distributed hypermedia application. But there's more to this story, because you may not have a distributed hypermedia application. That may not be what your business needs. I can't tell you that's what you need. You have to start with the business problem you're trying to solve. So cloud computing, one of the challenges of cloud computing is it's a lot of different things, right? A lot of different, you could be virtualizing your storage, your virtual machines, your software, your platform, right? There's a lot of different things you could do with the cloud environment. This is one thing you might need to do, but you need to know, based upon your architecture and your business needs, where you require scalability, where you require elasticity, and which cloud deployment options are right for your situation. So I just described how you would deal with a particular one, a distributed hypermedia application, but that's not necessarily true in your case. So you don't necessarily know cloud is the answer unless you understand the question. So try this on Amazon. Now, I heard somebody tried it on Amazon, the French version, and it didn't seem to work. But Amazon.com, which I guess is the American version, I don't know if you have a Singapore version, but make sure you're on the American version, because that's the one that, that's the biggest version. And try this at home. So here, what you do is, let's say you go to Amazon, and you put something in your shopping cart. Now, launch 2 different browsers on 2 different computers, or 2 different, Explorer and Firefox on the same computer or whatever. Put something in your shopping cart, go to the other computer and reload, and it'll still be, the count will change. The object will be in the shopping cart. Both browsers will show the same item in the same shopping cart, right? Now, begin the purchasing process on one browser. So you go through the step, you say, okay, here's my address, here's my credit card information. Now they give you a chance in the middle of the application to change the number of items you want to order. You did want 1 copy of the book, but now you're going to buy one for your mom too. So on one browser, you change the count to 2 items. Now reload the other browser. It still says 1 item, where you have inconsistent data, right? Why? Because Amazon does it this way. They spawn a cloud instance to maintain, to run the shopping cart application once the customer is in it. But as a result, because they're partition tolerant, they cannot achieve immediate consistency. The consistency, it'll be eventual, right? Make the purchase and the shopping cart will be resolved, but in the short term, you'll have inconsistent data. Right? One browser will show one item in your shopping cart, another browser will show two items in the same shopping cart. But that's the way Amazon works. So could you go into Amazon's web pages and screw around with hidden field data? Yeah, but the worst that can happen is you'll screw up your purchase. You're not going to be able to steal money from Amazon because they thought about that. All right, well, that's it for my second talk. So all that's left is more question and answer. Yeah. Uh-huh.
You're saying that there's difficulty in doing that in the session, in the application server side, right?
Well, there's challenges. If you maintain state on the application server, there's a few different problems. One is, what if the application server crashes? Well, where is it stored, and is it current states, right? So if you go into the Oracle ESB, for example, you have to take thread state and you have to dehydrate it, write it to the hard drive, and then you have to reconstitute it. And if you've ever been to an Oracle SOA class, it's like half the damn class is all about state thread management. It's such a huge hassle. And it doesn't solve some of these fundamental problems, because now if you were to take that and run it in a cloud virtual machine instance, then you'd have the Neo is the one problem, because now you spawn a thread that represents the client state for their particular process. That's only running on one virtual machine, right? And if the client goes to some other virtual machine, it won't know who they are.
But what about, say, grid-based session failover?
So what was that?
Grid-based
session failover. Well, that may be that synchronization that I was talking about, right? So there's different ways of handling synchronization depending upon the situation you have. But so
you still have to manage it at an application level.
Right, but there may be certain aspects of resource state that you're maintaining. And
my concern is that in pushing the state information to the client, we are effectively increasing the load. Because the state information has to be moved to and fro between the browser and the server.
No.
As a result.
At least in terms of previous example that I showed you, right, night talk.
By the word moving the application state to the client, you see, the components that are communicating already have the state there. You don't have to do too much stuff explicitly. It's not as if the state is in the center and you're moving it to the client. That's not what Jason means. He says the whole design of the system is such that state is just at the client level. That's the meaning of the term. The state never hits the server. It's not as if it is in the server and you're moving it. No. It's what the term really means is it's just always at that level. So there is never any issue of the client application storing away some state in the server and then wondering what happens when it crashes, etc., etc., etc. As Jason had said, after class with Oracle SOA depends on state management, which takes up a tremendous amount of time, and then you have to buy a lot of hardware.
If you look at the messages, which you can think of when you view the source on an Amazon webpage, where are they putting that state information? Well, they're putting it in hyperlinks. So you see a hyperlink, and there'll be some sort of state key in the hyperlink, and they may not actually have REST-based URIs. They don't go that far. So they'll have all this stuff after the question mark. Well, that's actually in the hyperlinks. So the hyperlinks maintain the state. But keep in mind as well that a web form is essentially another type of hyperlink, right? The action is the URI, and there's the hidden fields that also contain some of that information. And if you post that form, then that information is sent along. So the state information is maintained in the messages, because those are the representations, the request and reply messages. So if something goes down, as all that information is maintained in the message, which is still in the browser. So the middle tier can go down, come back up, and the user clicks a link or submits a form, and the application running on that middle tier knows everything it needs to know, because these messages are self-descriptive. Remember, self-descriptive messages is also one of the REST constraints.
So how will you survive that browser
How do you survive a browser crash?
Since it's all in the browser, that's us.
If it crashes, the data, the messages from one step to the other are always written to persistent storage. So if the equivalent of the browser crashes, it's like saying, to give you an example on the Fiorano USB, it's like saying that the components that die, if the component itself dies, if the service dies, it's exactly the same thing as saying the browser crashes. The message instance at the time that it died is in persistent storage. When the component is fired up again, it picks up the message.
Yeah.
So you don't lose. The concept works.
Well, that's part of the power of having a queuing-based backend.
Yeah.
Right. And that's one of the things that Fiorano in particular brings to the table is because it's based upon queues. Well, queues guarantee delivery of a message. So if the browser crashes and comes back up, well, the message is still waiting in the queue. Right? Now, the Amazon website's a bit different, right? If you're in the middle of a purchase and your browser crashes, yeah, you have to start over.
Yeah.
Right? But
It doesn't have the full queuing mechanism. If you have the full asynchronous queuing mechanism built in, you could literally pick up exactly where you left off.
Right, and that's part of what queuing brings to the table that, say, a request reply like the website I was talking about, the e-commerce, doesn't have. So, there's, it gives you an additional level of resilience.
Yeah.
Can actually REST be used to get rid of the application server and have the browser connect directly to the services?
Well, in the REST-based SOA approach, you have an intermediary that provides the endpoint, right? That has a uniform interface, and the intermediary is now responsible for routing requests as appropriate. So it can route it to
Some
queue.
routing has to be done.
Right.
And that's what, for instance, in our case, there's no application server with Fiorano. It's just distributed JMS servers. There's no concept of an application server.
I'm talking about a 3-tier application where you have a web server, application server, and an ESB behind it. It could be Fiorano or something. So typically, web server is serving all the static content, and
You can get rid of the application server. You can get rid of the application server. Absolutely. You can get rid of the application server. You do not need the application server in that case, because the ESB will maintain the state in its services. We have lots of applications like that. You'll have a web front end talking to a service, and then all the state is in the services, like the REST-based SOA approach.
Right, so a traditional application server deals with state by spawning instances that correspond to individual users. So you have a number of thread instances, and so that's why they have performance limitations, right? A single application server can only support so many users at a particular point in time, and if something goes wrong, you have all these issues of finding the appropriate thread that corresponds to you, and that's where all these issues come about. So if you maintain statelessness in the middle tier, well, it doesn't even have to be an application server in the traditional sense. So it could be, a feeder on a bus. It could be, just a simple, a servlet engine, right? That's all you need, right? It's something that can run PHP. It might be all it is. So it could even be a kind of web server, right? There could be the web server there. It doesn't even have to be anything fancier than that. Depends upon what your application looks like. Yeah.
Now that you're putting all the data and the operations in the message is going to be pretty heavy. Is there any best practices on what kind of hypermedia to use so that we can get maximum performance? Well,
it could be, but it isn't necessarily heavy. Because you have so many different kinds of representation, different media types you could use. That's one of the things we were talking about before the break, right? That in the web services world, you default to XML, and XML messages, especially when you're dealing with web services and SOAP and all that, they get really big really fast. And now it becomes this huge nightmare. But you don't have to use XML. You could use a lightweight representation, a JSON media type or something like that, that it only has as much information as you need. So maintaining state information is often as simple as putting hyperlinks in your JSON representation. And actually that's something that, it's on one of these slides here, which one was it?
The biggest performance hit is XML, actually. A lot of time goes in parsing and managing and the size and a lot of things like that.
Well, this is right here.
I mean, you can't get away from that.
So one of the things, and I don't know if you noticed when you saw this, see that the request is simply the hyperlink, the URI. Well, it's really just a URI, and the response has a request in it. I don't know if you noticed that. Here's the request. This is the only reason that's there is because the document has essentially the entire history of the interaction between the client and the server. But it's just a single line, right? This isn't that heavy, right? So you can have some interactions, and each interaction puts some more information into the message. The idea is the message is the document, is the interface, right? That's one of the things that Atul said. What he means by that is, if everything crashes, all you have is this document. It tells you everything you need to know to pick up where you left off, because all the requests and replies are right in there. So it's completely self-descriptive in that sense, that this is all you have to worry about.
Yeah.
So when you combine that with a queuing infrastructure that guarantees delivery of messages, so if something crashes, this thing is still there waiting for you. This has all the information you need to pick up where you left off.
And the
and
queuing...
it's really very lightweight.
Right. And the queuing ensures that you get the last document before the crash.
You get the right one.
So you never lose a message.
Right.
So that's why the biggest best practice is spend a tremendous amount of time designing the documents properly. This is the key.
True, but the transaction has to be maintained in a particular manner. If that is the case, if we are able to be going up and down for a different set of data, then to maintain the transaction and then the application.
Yeah, that's part of the document design process. Yeah, you have to walk through it and say at this point the document will look like this, that point the document will look like that. It's one of the important best practices. Spend a lot of time. So in fact, if the system goes down, you should be able to actually, ideally the human being should be able to read the document and make sense of it, which is certainly not the case with a lot of large XML docs. Right.
And remember as well that, we're relying upon the document to be the interface, but that means we're not relying upon traditional operations, right? Because we get post, put, delete. That's all you have to worry about. And so your resource just has to know how to get post, put, delete one of these things. But this is the interface, right? You don't have to worry about a traditional API. By traditional API, application programming interface, you think of a traditional API, you have function calls with parameters, and we're getting away from that. We don't have function calls, we don't have parameters, right? There's none of that. We have documents, and we have get, post, put, and delete. Add that to a queuing infrastructure that provides guaranteed once and only once delivery of messages in the proper order. That's all a queue is, right? Then you have this fault-tolerant, scalable infrastructure at a fraction of the cost of a traditional heavyweight process engine type infrastructure. And it's also easier to architect once you get your head around what it means for the document to be the interface. And then you spend your time architecting the document, which is a whole lot easier than dealing with thread management in Oracle. Good luck with that.
Yeah, that's a big issue. It's a lot bigger issue than it seems. It's not just Oracle. It's every ESB out there, because everyone relies on the concept of a BPM-centric flow, basically. So the dehydration is not something that people talk about when they're selling you the product. Trust me. Because what happens is the sales guy puts up this beautiful chart, so you just drag, drop, connect, and it's all done. Hey, Chip, it's done. There's no problem. It's all there. You got to get under the covers, right, to understand it. There we go.
Yeah, so it's... What's that? Uh-huh.
Cloud instance which can be spawned with the same representation. So this is a capability of the cloud vendor, or is the application needs to build in this capability?
Let's bring up that one. That's this one here, right?
Yeah.
Well, the cloud provider, build the whole thing, there we are. The cloud provider is really just providing the capacity, right? So they're providing virtual machine instances or database instances, etc. And they're providing the automated elasticity. So that if I need to spawn a cloud instance, I just say, I put in my application logic, spawn a cloud instance, and then the cloud provider takes care of that for you. But it's, keep in mind, cloud computing is still an emerging approach, so there may still be complications, but that's the way it's supposed to work, and that's what they're trying to achieve. So, I don't know if that's it. Is there more to your question?
So it's part of the cloud render. It's a capability given for that.
Well, the elasticity aspect, right? Essentially, they're providing you with a set of cloud APIs that enable you to program the cloud the way you want. And now it becomes a question of how do you handle the automated configuration and make that part of essentially your application logic. So it's a different notion of coding. This is one of the things I've written about in some of my recent research. Right? A traditional coding context, you have the code which runs on a server or some piece of hardware somewhere, and it's separate from provisioning the box. In the cloud environment, how we provision the box is part of how we want our application to behave. So we have to have the appropriate configuration as part of our application functionality. That has to be automated. So when we spawn this new instance, it has to bootstrap itself, right? It comes up, it says, well, what am I? Oh, I'm supposed to do this. Where's my data? Where's my application? Where's this? Where's that? And it's supposed to do all that automated. Well, how does it know? Well, you have to configure that. You as the system programmer has to configure the cloud capability to handle the bootstrapping and the provisioning. And this is a part of working in the cloud environment. So some of it is operational. And so we have developers getting their arms, rolling up their sleeves and getting into the operations. And how do we deal with cloud instances in the runtime environment and handle operational configurations? Now that becomes part of the developer's role. And so we have this sort of new world of DevOps where developers and operations are becoming all part of the same team.
I mean, a good example is if you take the context of the REST-based SOA and the distributed architecture that Fiona talked about, right? That you got multiple services, right? Now the way it will work in the cloud context is you have multiple peer servers pre-set up. Let's say 20 peer servers. And each peer server can run maybe 20 services. So if you suddenly need to run 400 more, say 50 more services and 2 of your peer servers are full, your app is essentially a distributed app. Different components are running on different peers, right? So the additional 40 or 50 components that you want to start off, you have to use some APIs to tell them to start off on a different cloud peer. But essentially, the cloud peers are the infrastructure. They don't manage the application state. The application can be thought of as a distributed application where the services are sending messages to each other and all the stuff is managed at that level. It sounds a bit complex, but it isn't. You just got to
it's not that it's
actually pretty
complicated. In
straightforward.
fact, it's simpler. It's just that it's an entirely
It's a different way of thinking.
It's a different way of thinking. So many people, who've been programmers their whole careers, or used to be programmers. I'm sure most, if not all of us, either are or used to be programmers at some point, right? So we had this sort of functional imperative programming context to how we learned how to program. Right? Imperative programming basically means that you have a line of code that does something, and you go on to the next line of code and do it. Right? That's imperative programming. Well, obviously, that's how you code, right? You write a line of code, it does something, and you go on to the next line of code, it does something, right? And then functional programming is a type of imperative programming, or is it when you have a function, you call the function, and it replies. Well, in actuality, functional programming is actually a subset of declarative programming. Because when you're calling a function, you don't know what's going on inside. Essentially, you have this function logic. But that brings this RPC notion to declarative programming. What we're talking about here is fully declarative, right? The document has all the information, is self-descriptive, has all the information we need in it. We don't need method calls. We don't need traditional operations. We don't need functions. We don't need to think about the application in the context of imperative programming.
Yeah, because the application consists of a bunch of components which are running on different boxes. It's actually a distributed system.
Right. If this is the interface, the document is the interface, this is fully declarative. Right? This does not tell you how the code should be written. It doesn't tell you, if, then, while, do, etc. This is just the document. But this is all you need to run the application, right? Because the hypermedia is now the engine of applications. It's a different way of thinking about what it means to program.
So there's multiple concepts. One is the declarative style. That you give the document to a component and it will run it. The other is there are multiple instances on different parts of the cloud, components that are running, right? And they tie together.
I'm just trying to understand the state because you're moving to the client. So if let's say I use an example, on the one page, you add an item, you click, you add an item, you move on to the other page. The URI actually changes. So what happens if the user were to press back page, right? Which state will they actually retain?
Well, you have,
On both the pages it will
you
have
have
the data.
the expected behavior of the back button, which will take you back to the previous representation, which may or may not be what the programmer wants the behavior to be. And if it isn't, then you have to kludge the back button. But that's something new. I actually wrote something about programming the back button back in 1997. I remember that. I think the article is still up there.